It's a pleasure for me to have David here, and I would like to leave him the stage.
What I'm going to talk to you about is how we can get the most out of digital outcrop models. I've been working in the field of digital outcrop geology for quite a long time now, from early days of differential GPS through to using LiDAR systems, and then more recently photogrammetry. It's going to let me move. Right, so hopefully you can see there's an animation on the screen now. This is kind of where we are at the moment with digital outcrop models. We're able to build very high resolution models of outcrop data, do interpretations on them, make very accurate measurements, and get pretty close to the kinds of detail that you can get in the field. Still a way to go on grain size, but we're gradually getting there. So when I started working with outcrop data in about early 2000, I soon realized that I wasn't able to do what I wanted with the outcrop data sets that I had. So I started to develop a piece of software that allowed us to do that. And that was VRGS. So it first developed in 2003. The first publication using VRGS was in 2007. And then in 2020, just at the start of the first lockdown, I took a career break from my job at the university to put together a company to commercialize VRGS, and I've been working on that since then. I am currently still at the back at the University of Manchester, sort of temporarily, but I will be returning to VRGS Science full time, the company, in a couple of months. So there's a lot more to be developed and a lot more to be done. So what you're looking at here is a digital outcrop data set integrated with a fairly high resolution LiDAR elevation model from Northeast England. And you can see we can get quite a lot of information and extra annotations in there. So what are the problems we have when we deal with digital outcrop data? So one of them is we have large volumes of data. These outcrop models can be quite big. We start to integrate with elevation data, and that gets quite large data sets. We're dealing with data from multiple sources now, so from LiDAR, from photogrammetry, from GPR, samples, all these sorts of things. So we have to integrate lots of different data types. We have to work on a range of scales, from the scale of grain size through to regional scale, all in an integrated framework. When we work with outcrops, and something that quite a lot of field geologists tend to ignore, is we have a lot of uncertainty. We only ever see in an outcrop a very small proportion of what we're actually dealing with. Even when the outcrops are really well exposed, that slice of the outcrop that you see through that 3D volume still only represents a very, very tiny proportion of the volume that you're dealing with. And there are lots of uncertainties associated with that. We need to be able to extract statistical information. A lot of what I've done in the past on working with outcrop data sets has been really to drive statistical models and stochastic models for understanding subsurface fluid flow. And to do that, we need good statistical data sets, and we need large statistical data sets. And then the other problem that we're having sort of more recently is, travel. It's becoming more expensive to travel. There are environmental impacts to be considered now when we're traveling to different countries to see different outcrops, and there's safety and time to think about as well. So, going in the field can take up quite a lot of time. So what can we do to make that time more effective? But of course, the travel thing applies very, very greatly to if we're discussing planetary geology. It's quite often, you know, they're places that we're not going to be able to get to, not for a long time anyway, as the general population. Thinking about the data a bit more, the kind of data that we deal with, I've mentioned LiDAR and SFM. We have GPR, not so applicable in planetary at the moment. We have photographs, which are becoming more common to get from rovers, like the Mars rovers. We have elevation data, and there's very good elevation data for the Moon and for Mars now. We have thin sections that we can integrate into our models, traditional mapping techniques and elevation model mapping techniques. And on the planet Earth, we're very, very fortunate to have GPS to georeference our data sets, which of course we don't have on other planets yet. And the pictures here is one of my first field GPS unit, which took, I think it's something like 8 AA batteries and had a run time of about 2 hours on those. So it was but very high tech at the time. I'm going to take you through a few case studies. So we're going to look at different ways in which we can use data that we've collected remotely using LiDAR and structure from motion to give us more information about the geology that, you know, that we're investigating. So I'm going to take you back to the early 2000s for a project now. And this is Wadi Knuckle, so out in the Gulf of Suez, the Suez Rift. And this project was looking at reservoir scale heterogeneity, so understanding how fluids would flow through these kinds of rocks. Here we've got the Suez Rift. There's two big fault blocks, Hammam Faraon and El Kar. We're just on the southeastern corner of the Hammam Faraon fault block in a location called Wadi Knuckle. And that's what we've got in this top right-hand image here. This is a spot satellite image. Sorry, no, this is QuickBird satellite image overlain on a digital elevation data set. The red dots are where we collected LiDAR data. So we took our laser scanner, an old Regal LMS Z420i, which was brand new at the time. Took it around, collected all of these, merged the data sets together to produce a very high resolution map of the outcrops all the way around the study area. In terms of the stratigraphy, we're in the lower Miocene, right at the knuckles in the lower Miocene, and we're right on the pre-rift syn-rift contact here. So just going into so we're early syn-rift in the knuckle formation. Along the side of the outcrop here, we have the knuckle fault. And then through the middle, parallel to the knuckle fault, is a synclinal axis running like this. And the knuckle fault is active at the time of deposition. And at the bottom here, you can see the LiDAR data set with all of these measurements that we made on it. Now, if we look in a little bit more detail, this is what we were able to get in terms of the structural geology from all of the LiDAR data. So each one of these is a structural measurement derived from the laser scans. Now, if you're out in the field, in this field area, it's actually really difficult to make a structural measurement because these are all tidal sediments. You've got a lot of interbedded mudstones and sandstones. In fact, they're calcarenites, so calcareous sandstones. And they weather quite a lot, and it's very difficult to find somewhere on a small scale to get a structural measurement from. But when you're working with digital outcrop data, you can actually make a measurement over a slightly larger scale. So if you can see the geometry of a bed over a few meters, you can make a measurement across that few meters. And if you can select 3 points along a bedding plane, and those 3 points are not in a straight line and in a triangle, you can calculate an orientation from them. Once you've done that, you can get your strike and dip measurement. So that what was done here. And we were able to show that the perpendicular to the main fault running down the eastern side of the synclinal of the rift here, we've got these fault perpendicular anticlines and synclines. Now, these had been identified before we had done this work, but it was only thought that there was a couple of them, but it turns out there's a lot more. And also previous work showed these fault perpendicular anticlines and synclines were possibly continuing over into this side of the study area, whereas our data showed that the main synclinal axis is acting as a structural barrier to the propagation of these folds. So it limits the folds onto this side of the on the syncline. And then also we've got a rollover anticline coming into another fault that's along down the bottom here. This is the Baba-Markat fault. So we can just compare that to the original interpretation, and you can see that by integrating the digital outcrop aspect and being able to make measurements from areas that you couldn't physically get to, we're able to shed a lot more light on the geometry and the structure of the knuckle syncline. So our next case study is looking at fracture mapping and fracture statistics. And for this one, we're going to head away from Egypt and we're going to come back to near Manchester. Just to the south of Manchester, there's a set of old mines. They're disused now. They're copper mines. They have a very long history. So, early sort of Bronze Age kind of evidence of mining there, right the way through to, I think they were closed in the 60s. But there's an extensive sort of set of these tunnels in the Sherwood Sandstone, just to the south of Manchester. Very difficult to get to. To get into them, you need to have assistance from the local caving society. And we were very lucky that they helped us 1 year for one of my PhD students to actually study the fractures within there. So we're in West Mine, and we're actually just looking at this part of West Mine, very small part of the whole mine network. Again, this was done with the laser scanner. Very difficult to do photogrammetry in a mine like this because it is completely dark. There is no light in there whatsoever, apart from artificial light that you take with you. If you turn your head torch off and put your hand in front of your face, you can't see it. It is that dark, no light at all. You could use a flash gun for photogrammetry, but you get problems with the flash not going far enough and drop off in the light and the images and all sorts of things. But because your LiDAR system is an active system, it provides its own energy and forms the laser, you're able to map very effectively even in those conditions. So we carried the LiDAR down and we collected a set of laser scans throughout the mine, merged them together, and we were able to create a very nice 3D model of West Mine from which we were able to go in and interpret key stratal surfaces and make measurements on fractures. So here's a animation, a fly through of the West Mine data. So point cloud from the laser scanner. The horizontal surfaces that you can see are key stratal surfaces, but in this case, they're bed set boundaries, which we were using to subdivide the model into zones. And then the squares that you can see are fracture measurements. The PhD student who worked here on this project, he also went down and collected traditional scanline fracture statistics, which involves walking along, making lots and lots of fracture measurements. That again required the assistance of the local caving club. For every one of us that went down there, through health and safety requirements, we had to have 3 of the caving society with us. So, but they were very happy to come and help out. So my PhD student went down, spent 3 days collecting fracture statistics from this mine, and then put them all together. So we've got here the fracture statistics from the scanline surveys. And first thing to note, 3 days work in the mine, 622 measurements. From the LiDAR derived fractures, I mean, okay, you've got to take into account that we had a day of data collecting the LiDAR data, but then there was also 1 day of interpretation to collect 1,377 fracture measurements. We compare the results of the manual survey with the LiDAR derived ones, get very good match, as you would hope. There are some differences. You can see that the LiDAR derived fractures are a little bit more diffuse, a little bit more dispersed. That's probably because of the resolution of the scanner. Maybe we're not able to measure as accurately as we can do on the outcrop. Scanners have improved a lot since we had this one, but we also had an idea that maybe some of this sort of more clustered data was perhaps an effect of human bias. So maybe rejecting some data points that you didn't think fitted in with what you were expecting, maybe. So it's something to always remember in the field. There can be a human bias effect in data collection. The other thing to notice is that there is actually a slight difference in the orientations. The LiDAR-derived fractures are slightly rotated anti-clockwise compared to the scanline survey ones. What we think this is, it was an error in our georeferencing of the data set. This is all underground. There is no GPS, so very difficult to actually georeference effectively. The way that we did it was to mark out a line of reflectors that the scanner could pick up in the mine itself, and then take a bearing on them. And we use that bearing to orient the direction of the data set, line it up. There was also a few old ropes hanging from the ceiling, which we took to be true verticals, as they would be under the influence of gravity. And there was a wall at the end, which was also vertical. So we had a variety of data that we used together to get it georeferenced. But I think our actual orientation was slightly out on our orientation line. So that accounted for the slight difference in orientations. Then we take of all that statistical information and build that into a stochastic model. So the Sherwood sandstones that we're looking at here are important in the UK for, they're from the south of England, they're the reservoir rocks for the Witch Farm oil field. But in other parts of the UK, they're very important aquifers as well. So knowing how fluid flows through them and understanding that flow process is important in many ways. So we took those data, we generated a model, and then we built both models from the manual fracture statistic measurements and from our LiDAR-derived fracture statistics measurements. You can see, looking at the two of them, that there is a slight difference between the two, but generally they were in agreement. Our third case study is looking at a different scale again, so going a larger scale now. Fracture mapping of sandstone intrusions. So this is a project that I worked on jointly with the University of Manchester and the University of Aberdeen, the Sandstone Injection Research Group. And we were out in California looking at the Panoche Giant Intrusion Complex. There's a couple of intrusion complexes in this area. So we have the one in the Moreno one, the Panoche and Moreno ones, and then the higher intrusion, the Toomey intrusion complex up here. What these are is a set of exposures where we've got the sandstone intrusions. They are similar to igneous intrusions, but they are sandstone, and they are sourced from sandstones lower in the system. The sands have been remobilized and injected into the overlying sediments, and they form sills and dikes very similar to igneous ones, but they're siliciclastic. The pictures that you can see here, well, the first on the left-hand side shows the extent of the outcrop, and the pins are the main study areas that we looked at in the field. But we've got 12 kilometers of exposure of these sandstone intrusions, and these images here, these are from Google Earth. Again, these are probably world view images. There you can pick up the bedding quite nicely, and particularly in this one here. But cross-cutting the bedding, you've got a lot of these features, and these are all sandstone intrusions that have been remobilized from the sediment below. In the North Sea, sandstone intrusions do have an influence on the way fluids flow within hydrocarbon reservoirs. So that's one of the reasons why we were looking at these. What we needed to do was understand the structure and understand the statistics of the structures to be able to model them effectively. And we did that by going in and measuring lots of statistics from them. So we can measure the orientation, we can measure the apparent lengths or the visible lengths, we can measure the thicknesses, and we can start to plot all of those together. And then we can start to try and derive from some statistics on the intrusions. And here we've got a correlation coefficient. And I think, the first thing that jumps out when you see this is how much uncertainty there is in this correlation. There's a big gap in the data here. There's quite a lot of spread, but this is sort of the nature of geology when you're working with real data, is that there are these wide spreads. Some of this will be down to censoring effects of the outcrop compared to the orientation of the intrusions. The intrusions are not always well exposed. The sediments are very soft here, so they tend to get covered up. A lot of we know that the length measurements that we made were nearly all apparent lengths. The thickness measurements were pretty good. The orientations were pretty good, but there is a lot of uncertainty in there. And really, we need to go in and fit in to get some more data to fill in the gap along here. But we were able to start to derive some, show that there are some relationships between the different parameters, width, thickness, orientation in the intrusion complex. We could then take our digital outcrop data sets and start to build geobodies using this statistical information that we had collected. So we can take a sandstone intrusion, map it, and then project it on its orientation into and out of the outcrop to give us a better three-dimensional representation. We can use our interpretations to create a classified point cloud. And then we can also use our interpretations to do things like intensity maps. So this shows a map of the intensity of intrusion across the model. So for the structural geologists amongst you, this would be a P21 map. So it's a map of the length of intrusion over the area, over a unit area. The classified data set also enables you to start pulling out some other statistics, like being able to work out what proportions are as well. But again, you have the censoring effects of the degree of exposure and the orientation of the outcrops to worry about as well when you're doing that. And then case study 4 is we're now going to head over to Spain and to the Huesca fan, and we're going to look at mapping geobodies. another approach that you can use with digital outcrop data. So we're here, Ebro Basin, in this sort of study area here. We're based around Huesca and Pereces, looking at the fluvial system. Similar kind of process, collecting both LiDAR and photogrammetric data. The yellow data points are laser scan positions. The red lines are where we've taken sedimentary logs and integrated them all into a 3D model. Taking all of that data together, we're able to interpret the geobodies. So in this case, a geobody in these outcrops are the geobodies of fluvial channels. And we've got single story channels and multi-story channels. And there's different ways you deal with different types of channel, but really what we wanted to do was understand the channel geometries, right? So at the time of deposition, what was the width of the channel and what was the depth of the channel? Now, you can't just measure the width of a channel from an outcrop, because for it to give you the true width of the channel, your outcrop has to cut perpendicular to the flow direction, to the axis of the channel. Any other cut is an apparent width that you would get. So it has to be in a particular orientation. You very rarely get that or in the real world. So what you need to do is when you're mapping the bodies, you need to understand, work out what the orientation of them is, what the direction of flow was in that channel. And if you've got the direction of flow and you've got the geometry mapped in 3D around the outcrop, you can use a bit of trigonometry to work out what the true width is. The problem is working out what the channel orientation is. These are meandering channels. By their nature, the orientation changes along their length. Also, if you take paleocurrent measurements from a meandering system, you will find they go all over the place. They have a very, very high dispersion. So what we did was for each of the geobodies where we could, we would measure as many paleocurrents as we could within the geobody. We would then plot those paleocurrents on a Rose diagram. We would take the most common paleocurrent orientation and use that as our most likely, and then use the others to give us a possible range of variation. So we would end up for every single geobody and a width that was based on the most likely outcome, but also a minimum and a maximum. So plotting all of that together, we were able to create a map or a graph of how the geobody geometries change throughout the evolution of the system. And you can see there's quite a lot of variability in here in this graph. Each one of the black data points is our most likely. So that was what most of the paleocurrents gave as a result. But the lines give us the range of possibilities, our range of uncertainty for each of these measurements. So you can some are quite small, some are quite high. But again, understanding this uncertainty in your data and realizing that, you know, a lot of these measurements you make aren't always going to be 100% correct. There are errors in there is really important, and making sure you account for those and show those is really important. Now, when we've got all of this data together and we've collected all of these data sets and done our analysis, it then allows us to do things like virtual field trips. Being able to take people to see outcrops that they wouldn't normally get to, or when you're teaching field work and you want to give people an introduction to a set of outcrops before you actually get there, that kind of thing makes teaching geology in the field so much better, so much more effective, because people have a level of understanding when they get there for the first time in the real world. So virtual field trips are really about trying to bring the field into the office. So to prepare for your own, for real field trips, pre-field trip, post-field trip, but also to visit localities not otherwise possible, which is planetary geology, as well as a lot of the geology that we have around the world. So why we can use VR, and a lot of us have been talking about VR, and there's been a lot of discussion and things in the news about it. But why should we use VR? How can it help? Well, first of all, it's a great way to visualize your data. Just to be able to look at your data working in virtual reality gives you a much better perspective, and it lets you look at the data in a slightly different way than you would do if it's just on desktop. There are advantages to both ways, desktop and VR, so linking them together is a great way to go. We can do interpretations in VR, and again, sometimes the different perspective that it gives you makes your interpretations easier. It's not you wouldn't spend a lot of time interpreting VR, not at the moment. It's the kind of thing you do short spurts on, and then most of your interpretations done on desktop. It's a great way of validating data. If there's errors in your data, sometimes if you look on a normal 3D view on a desktop or just on your normal screen, you can't see the errors. And you put your VR headset on and look at the data, and errors in the data jump out at you, particularly in digital outcrop data sets. When you're merging different data sets, sometimes it can be quite difficult to pick up mismatches in certain types of data, but you go into VR and it's easy to see. There is also scale, understanding of scale. I had a postdoc student quite a few years ago. It's actually back in the days of the first example that I showed you, the Knuckle project, the Rift Analog project. He spent 3 or 4 months interpreting the digital outcrop data before he went out in the field. When he went into the field, he had an incredible understanding of the field area. He knew where all of the different key stratal surfaces were. We could walk along a wadi and he would be able to say, round the corner there, this surface disappears underground. Round that corner there, there's a tree and there's a rock next to it. His knowledge of the area was just amazing. But the thing that he didn't get was the scale. He just hadn't got from the digital outcrop data set, even though there were scale bars on it and he was actually making measurements. When you're in the field, you don't get the impression of scale that you do in the field. You get that in VR. If you're standing at the bottom of a 120-meter cliff in VR, it looks like a 120-meter cliff. If you're on desktop, it just looks like could be any size. So that's why it's important to use it for scale. And then, of course, there is the training aspect of it, as well as being able to visit, versus different field areas and look at them. But one thing I will say, that this idea of using VR and immersive visualization, it's been around for a long time. And we've been here before, twice in the past. Back in the 90s, in 1993, there was a game show on UK television called Cyberzone, which was based around using VR, very early VR, with the kind of headsets that were about the size of a car. It was awful. It never got past 1 season, but that was, actually using VR in a real setting. And then in 2002, there was an immersive visualization system that came out of Norsk Hydro, which was a Norwegian oil company. So they developed this system that ran in caves, so rooms with multiple projectors, and you had to have stereo glasses on with the shuttered lenses. It's very effective, but took a lot of money and a lot of cost to actually set up and run the visualization rooms. So we've been here before, and we're now progressing into something that's a lot more usable. So some of the challenges of using VR: comfort. but having a headset on for a long time can be quite uncomfortable. There is the cost of it. Headsets are getting cheaper, but to do the kind of VR that you're seeing with these models here, this is really, probably what we would call enterprise grade VR, where you need a lot more processing power than just a headset on its own. So you need a machine with a computer with a really good graphics card. You have to worry about high frame rates, much higher frame rates than you would do if you're on desktop. You need to, a VR headset needs 90 frames a second. Then you've got two eyes, so you're effectively having to render at 180 frames a second. That's quite fast. Cyber sickness is a problem for many people. You feel ill after using the headset. Some people, it doesn't take very long for them to feel that. Usability. How do you actually manipulate and interact with the environment in a way that's useful? There's this idea of consumption versus creation. So a lot of people have talked about using VR for interpretation and for making things, but really they're designed for consuming data, for visualizing it and looking at it. Your desktop PC is more like the thing that you would use for content creation. And then for us, for geological purposes, VR actually works best in a range of about 0.5 to 5 meters within the field of view to get the really strong VR 3D effect, but you still get the impression of the scale at distance. So there are some challenges, but challenges are there to be overcome. And so we would use our virtual field trips to do training, help us reduce costs by making our time in the field more effective. I put this slide in because when we do field trips, quite a lot of time in a field trip is actually spent at the outcrop, talking about the outcrop with a whiteboard or something like this, with everybody not looking at the outcrop. If we can translate some of this component back into the lab before we go, we actually spend more time looking at the rocks themselves, which is, as geologists, that's really what we want to be doing. So it improves our efficiency, our field trip, and of course there is a big safety aspect to it as well. Some of these outcrop models, you can use them to better understand what is dangerous about particular field areas before you go to them. One of the data sets that I use for one of our field trips, after I collected it, I realized that one of the localities that we tended to stand under quite a lot, when you looked at it in the 3D model and got a different perspective on it, some of the rocks above it didn't look particularly stable. So now I keep the field trip away from that point. So multiple uses for digital outcrop data. And seeing as it's planetary, I thought I would just show a little bit of a planetary example. I haven't done much work on this particular aspect of digital outcrop geology, something that I'm certainly hoping to develop a lot more in the future. But here's a Moreau Patera dune monitoring project that was done looking at this this crater here, and we've got these absolutely fantastic dune system that's migrating in this direction. And I think this is just great, where you've got the dunes falling into the crater, filling it up. So the crater is acting as a sink for these sediments. And then on the lee side of the crater, we've got no dunes at all. So it's a fantastic example, but we can then take this, so I should say this is NASA HiRISE data. The HiRISE data is available to download. There's quite a lot of elevation data available. You can take that elevation data, import it into VRGS, and then you can start to do things like this. So this is a dip map. So they're showing the orientation, the angle of dip of the surfaces. So we can put measurements on the crater here. So we see it's nearly 2 kilometers across and about 300 meters deep. And then as we go across and look at the dunes, we can see the slip faces on them. We could go in there and make measurements on them. measure the angle of the dip of the slip face, lots of different things that we could do, but it's a fantastic way of handling this data set. There's a whole range of different attributes that you can derive from surfaces, not just sort of dip. You can do things like coplanarity, collinearity, and there's a list of about 30 attributes I think we can generate now. That each tell you different things. The attribute maps that you can generate are also quite useful if you're looking at doing machine learning based classification of these kinds of data. So let's just briefly finish up and think about use of drones. And I think with some of the stuff that's gone on with the Mars rovers recently, you can see where this might be going, ideas might be going. The past few years, past 10 years, in fact, less than that, we've seen a real uptake in the use of drones for geological data collection. A lot of people just using them for taking nice movies and a few photographs, but with a little bit of effort, you can actually use them to generate some really high quality and very nice photogrammetric models. The consumer UAVs that we have now are really good for collecting this kind of data. The DJI the new Mini Pro that's come out is a fantastic tool for the field geologist, and one that you can just stick in your backpack and use when necessary. So we have on here, here's my old Phantom 3, which is the Phantom 3 Pro, which is a really good drone for photogrammetry because it's got a mechanical shutter. And then below it is the virtual drone in VRGS, which when you're doing virtual field trips, all of the field trip people, the people on the virtual field trip appear in VRGS as these drones. We can do other things with drones. There's things in development, like being able to do autonomous mapping. And the idea here is that you can just set a drone to fly on an outcrop, and it can generate a very simple model very quickly in a way that's safe, so the drone doesn't crash. But then it can use that simple model to generate a flight path to create a more complicated model and fill in the details and be able to accurately navigate around an outcrop. So there's AI-based workflows. There are a few companies working on this at the moment. So an example here is this company called Skydio. And they've used this kind of approach to build a model of I think this is actually a replica of one of the Apollo landing module. So it's in a museum. So they did an example where they flew a low resolution model, and then the AI used that to work out how to best collect the data to build a high resolution version of it. So that's something that we're going to see being developed more and more in drones over the next few years. There's also a real improvement and an increase in the kinds of sensors that we're dealing with. So not that long ago, it was just cameras, but we've gone to having thermal imagery. We've got drones with LiDAR systems built into them, collecting very high quality data. And I can go to a shop that's not far from here and just off the shelf buy a drone that is multispectral, because not very useful for geology. It's the wrong components of the spectrum. But the thing is, these have been come into use and come into sort of being easy to get over a very short time. We're only going to see an increase in those kinds of sensors and improvements in them. And some of the things that are really interesting are sensors that are in development, like MEMS sensors, these micro electromechanical systems. So this is a gravimeter. Gravimeters are normally much bigger than this. Being able to have something of this size that you can use in a drone eventually to be able to do, say, gravity surveys or magnetic surveys or other kinds of surveys. It's a very exciting time for geoscientists and for many other scientists as well. Why does this matter? Why do drones matter? Well, of course, we now have drones flying on Mars. This is Ingenuity, as I'm sure all of you know. I think it lifted up about 5 meters, turned around and landed again, but it's a start. And I have no doubt that the plan is to develop this technology to do more kinds of data collection in the future. So really exciting times ahead for digital geology, not just on this planet, but on other planets. There are so many exciting data sets that we've got there already to look at, and there's so many new data sets that are going to turn up over the future. People are now doing photogrammetry with the Mars rover data and reconstructing outcrops. If you want to try and do photogrammetry with some of the Mars data, if you go to the NASA website and look at the easiest one to work with is the descent of the most recent rover, and get the images for that. And that's quite easy to build a photogrammetric model of where it landed based on those. And that's it. So I hope that's given you a feel for what you can do with digital geology, the sort of measurements that you can make, the kinds of data that you can use, and maybe a little bit of an idea of how we can apply this off-world. So thank you for your time. If you want to get in touch, find me on Twitter at VRGS Science. On LinkedIn, so I have my own page and the company page, and you can always give me an email at the company email, david@vrgscience.com, or find me through the University of Manchester. If you Google me with Manchester, you'll find me. So thank you very much for listening, and I hope you enjoyed it.